this official, happy not garbage day. Happy Thursday instead. It's very important. Let's see, can one of you say hi so I can check the recorder, please?
Hello.
Perfect. All right, we should be capturing everything then with that. Let me get this thing out of the way. So what do you remember from last time? Let's start with a little review slash memory jogging exercise. You can talk, you
I
can type.
remember that we can't always use person mean centering,
Yeah.
but I'm needing to remember why.
Oh, because that part was still coming. So that was like the take home message at the end, designed to get you to come back for today. To leave you hanging on a cliff, you know? Yeah, so that's good. That's the last thing that we talked about. So we reviewed the idea of time varying predictors to start with, and how our primary concern has been, let's say, has been to ensure that between person information is separate from within person information and setting up the variables to contribute to the model. That is important for many reasons. Conceptually, the reasons that make people differ from each other are different than the reasons why some occasions are different from each other. So, like from a causal inference standpoint, like these are different processes operating on different levels. But just from a math standpoint, slopes are unstandardized. So it's unrealistic just based on the observed standard deviations in your x's and your y's that you would end up with the same slope at level 2 as at level 1, just because of the differences in the scale of what's happening at each level of the model. So more often than not, you will see between effects differ from within effects. And we have a couple different ways in which we can do that. What's the easiest way, the way that is the least challenging to screw up? You're putting time varying predictors in the model. What would I recommend to you in the vast majority of cases?
Person mean centering or variable centering?
Yeah, and why
Or
do I like that?
because it like fully separates the level one and the level two from each other, and it won't get messed up if you have random effects.
Ah,
Because
very
it
good.
effects you can derive it the other way, but not necessarily in the random effects.
Yes, indeed. So let's go with a picture for this here. Go with slide 4. Yeah, the idea is that when person means centering, you are doing the work on the front end to ensure that you know what you're getting on the back end. So we separate out what is supposed to be just within person level 1 time varying fluctuation information. We do that by taking the OGX minus the person mean. That goes into the model as the level 1 box. That captures the pure level 1 effect. And if you don't put that in, you're assuming it's 0 just like normal. At level 2 then, the idea of between person differences in the mean of this variable over time. That's what this green box is. And so we put that in, and that has the between effect. And if you leave it out, you're assuming it's 0. So in this setup here, we're focusing on fixed effects, meaning the part that's constant that everybody shares. The alternative way to do it, and the one that is more fraught with potential misinterpretation, is when you don't carve up your variables ahead of time and instead you let the model try to do it for you. So if you put in OGX and here, as it says on slide 5, minus a constant, it doesn't matter what the constant is. It could be the mean, it could be 0. You could leave it uncentered. For purposes of interpretation, that part doesn't matter. If we put that in, we would still put in the person mean at level 2, but then it takes on a different interpretation. It becomes the contextual effect, which is the level 2 effect after controlling for the level 1 variable. So we can solve the problem on the fixed effect side by adding in the person mean. But then, as I think you had said at the end of that, Taylor, what about the random side? Right? We have a level 1 random slope that if it is the person mean centered version, so backing up here, if it's the person mean centered version, then that's all fine because we've isolated theoretically the within person information in that level 1 predictor. We give it a random slope. There's no possible other interpretation than that random slope is between person differences in the within person effect. Cough, cough, homework question. Level 2 random slopes are between person differences in the within person effect, and that's all that it could be. If we tried to do a random slope for the OG variable, then it's actually doing two things at the same time. And so it's a smushed effect. It's just a different kind. And if we put in the original OG time varying predictor as a random effect, what it's doing simultaneously is two different things. One is what we think it's doing, which is introducing between person differences in the within person effect, but it is also introducing a heterogeneity of variance along the person mean for the predictor that's still buried in that level 1 variable. So it's a different kind of smushed effect. And there is really not an easy way to add a contextual effect to solve the problem on the random side like you would on the fixed side, because a random slope would be needed for a level 2 predictor and 2 level models. Exactly, that face is correct. It's illogical, but it is technically possible in terms of estimation. It just, you can't think of it as a random slope. You'd have to think of it as a heterogeneity term instead. It's changing how the variance is composed. So for those reasons, I would prefer person mean centering if we're doing time varying predictors that show fluctuation only, which is all we've talked about up to this point. Okay, does that help from last time? Because I know last time that was a lot. Just keep going back over it, keep thinking about it a little more. Do any of you have examples that you want to talk about, or specific like situations that this is making you think of in terms of your data, your projects, your life? Pondering. No, everyone's shy. Okay, I'm not going to cold call on anyone. I'll be nice. I figure if I start doing that, then you'll turn into all black boxes or just not show up. So I did make that deal with a student once. I had a student who ghosted me about halfway through the semester, and I was like, why aren't you coming to class anymore? This was before Zoom was even a thing. And he said, I'm terrified you're going to call on me. And he apparently had a lot of issues talking in public and not wanting to look silly in front of his peers. And so we cut a deal. I said, look, I promise I will never cold call on you if you promise to come back. And so that's what we agreed to. So if anyone wants to cut a deal like that, you can. But it's also probably in your best interest to volunteer things because it's free consulting. I mean, free paid by your tuition dollars, of course, but like free otherwise. Yeah, free. Air quotes around that. Okay. So everything that we've talked about in this picture here doesn't have time. Like the example that we went through with this was glucose and looking at negative affect as a predictor of changes in glucose between persons and within persons. And in that context of the study, it's what I would call pure within person fluctuation, meaning there is no time trend either on average or at the individual level. People are just sort of, some days are good, some days are bad kind of thing. So time isn't relevant necessarily if you're studying fluctuation. But then where folks run into trouble is when they try to apply the same idea to data that have systematic change on purpose. So like if I'm doing some kind of intervention study where I'm going to change how people parent their children, right? And they're supposed to get better at something, some kind of measure of parenting as time goes on. And then hopefully that will trickle down to their kid having better outcomes and growing more as time goes on. Like that's a very common type of design that I've seen. Well, person mean centering isn't going to answer the question, like do parents who improve more as a function of intervention have kids who improve more as a function of intervention? There's no improve in this model. And we can put improve on the y side just fine, right? If I want to quantify individual differences in improvement of some kind, what do I need to add? Individual differences in improvement over time on the y side. What do I need in my picture here to convey that? Random slope? What kind of random slope? We got to be more specific with the language from here on out. Survey says. Are you going to type, or you want to call it phone a friend? What kind of random slope?
I would like to phone a friend.
Okay. Who's friends with Erica? Or who would you like to make friends with? See, if we were in a classroom, this would be the point where I'd get like a ball and like we'd throw it to each other, like one of those things, you know? Do people still do that in classes? No? I remember that being a thing, like in grad school, to encourage people to talk. There'd be like a ball and you throw it to someone and they catch it and then it's their turn to talk. Random slope is right, but random slope related to time specifically is where I'm going. Because we could also have a random slope of how x predicts y as the time varying predictor. Right? Like, are some people more affected by negative mood in terms of how it translates to their glucose than other people? That's also a random slope. But random effects of time specifically is what I'm trying to get to here. So if there's individual differences in change over time and y, so improvement over time as a response to treatment in this context, I would need another green circle. I would have two kinds of between person variance in the model at a minimum. If change was some kind of nonlinear function or maybe a piecewise function for before and after, then I might need more than one random slope in the model, and then there'd be more than two kinds of between person variance to be explained. So we know how to do that, right? You do. I'm quite certain. I made you do it all last semester. You're good. Now, how am I going to make a box out of that? How am I going to get some kind of individual differences in change in a time-varying predictor? Faces are correct. What? Well, brute force is a choice. So I could take individual data and run each person through their very own regression model. I could output the slopes and save those as observed boxes and stick it in my picture. Now that is called slopes as outcomes. It's what people did in the 70s and 80s before software could catch up to do it the right way. It's not a good idea. The biggest problem with that type of approach is that you're losing all of the information about the error around your slope, right? You're pretending the slopes are perfect, and they're only going to be perfect if you have two occasions. They have to be imperfect in order to have room for a residual variance. So treating slopes as perfect observed boxes says, I've perfectly measured change for you with your 3 occasions. Kind of tenuous. So we don't want to do that. The answer is that we can't stick a box for change over time in here. Not if we're using observed variables to partition the variability in x. But we can if we switch from, this is slide 7, picking up here. There we go. We can if we switch to circles. So when I say switch to circles, what am I talking about? How would an actual methodologist describe this? SEM land, latent variables, yes. The idea is that we need to pretend, and not really pretend, that's what we're going to do, that x is an outcome along with y at the same time in the same model. That's how we do it. So conceptually, you can still think of x as a predictor, like how a parent improves as a effective intervention, then predicts how much their kid improves. Like, you can still talk about it that way, but from a modeling perspective, x is now in the likelihood. That means we have to figure out what its means, variances, and covariances should look like within x. How many kinds of between-person differences there are. Is it just an intercept sufficient, or is there some kind of individual change? How many kinds? All that stuff, we got to figure that out for x. We got to figure that out for y, and then we can connect the pieces. So where we're eventually heading, let me see if I can get a picture, is this place right here. This is slide 10. Circles. Change variance, change variance. So this is why random slope is no longer going to be specific enough, because guess what? This one down here, that could have a random slope too. The way that we talk about what within means has to change too when we start talking about it from this perspective. Previously, without the circles, let me back up a couple slides. There we go. Previously, we talked about the time varying information in X as being more than usual, and the level 2 person information in X as being more than other people. That works just fine if these are the only two variance components you need to describe X on its own. That falls apart a little bit once you add the circles. So now we think of the residual as something different. It's not being more than usual or less than usual. It's more than is expected for you based on your trajectory. So the words that I always use for this are, why are you off your line today? That's what the purple circles here are capturing. You are relatively higher at this occasion than your trajectory predicts. Are you also relatively higher than your trajectory predicts for the other outcome? That's going to be the within person effect, and that could potentially have a random slope. But then we have people between persons, people who start out higher. Do they start out higher in this outcome? If they change more in this outcome, do they change more in that outcome? And these paths in between here, these can be fixed effects, meaning they're slopes, or they can be covariances in SEM land, depending on how you want to set it up. If you just want to look at correlated change, but you're not thinking about one as a predictor of the other, turn it into a two-head arrow. You're fine. Okay, how are we doing? Okay enough?
So so maybe you're getting to this, but for the level 1, it's more than expected based on your trajectory. So like, how would we then interpret the other two, like within that frame of reference? Does that make sense?
So the green circles here are conveying between person differences in aspects of that trajectory. So an intercept for level differences at time 0, wherever you put that. So let's say it's usually the beginning. So this is a variable that is a level 2 person variable. So is this one. Each of these can predict each other. They can predict other things, and they can be predicted. The same is true for this new thing here. This circle right here where my pink mouse is, that's the thing that we need that person mean centering cannot give you. This is the idea that X itself contains individual differences in change over time, and that is a variable that you can then relate to individual differences in change in Y, or the intercepts, or other things, however you want. So I've got 4 between person variance components at the same time. In this picture, I've got 2 within person variance components at the same time as well. So time stuff could predict the purple circles, people stuff predicts the green circles, and the green circles can predict each other, and the purple circles can predict each other. Does that help? You want to see some pictures? No, they're fun, I promise. Hannah's like, no, I don't want pictures today. It's spaghetti plots. They're one of my favorites. So let me see here. Make sure I got... Okay, yeah. So I think I've hit most of the major review points. The other thing that I wanted to just reiterate, we talked about this last time, but I should still assume you don't have perfect recall of something that happened 2 days ago, right? That's still fair? Okay. The idea of what between means has to change if there's more than one kind of between. So if I just focus on the intercept part, if there are no individual differences in change in a variable, if the trajectories look something like the left side of this plot here on slide 9, then I could take between person differences as what they did at 12, what they did at 13, or any of these, and it's the same, right? People aren't going to shift around their rank orders because it's parallel change. Like if you're high at 12, you're high at 18, the end. Well, if we have individual differences in change, that's not true. So you could have, if you're predicting, say, some other eventual outcome, like in this context, this is parental monitoring over adolescence. This is simulated data based on real data that I played with a very long time ago. Let's say that parental monitoring might predict whether or not your child eventually gets a DUI or a minor in possession charge or something like that, like some kind of bad real life outcome. Well, here it's like on the left, I would say, okay, parents who monitor more are less likely to have a kid who gets in trouble. The end. But here it's like, no, parents who monitor more at 12 might have their kid be less likely to get in trouble. But like, what about 18? Like, if you're someone who decreases your monitoring over time, does that have an additional separate impact? Or if you're someone who realizes your kid's getting into trouble and you increase, does that matter? But if you just look at the cross sections at these ages, the kids are rearranging themselves because non-parallel lines eventually cross. So what you're thinking of as intercept has to become more specific. You need to know, is this the age 12 intercept? Is this the 15 intercept? Or is this the 18 intercept? Intercept differences are going to shift around as a function of change over time. So we got to become much more specific in how we think about it. So then, to be a little more concrete, give you a few examples. Multivariate relations is what we're talking about. So the transition from just predicting y and figuring out what piles of variance we need in y to then adding x into the model as an outcome and what kind of piles of variance we need for x at the same time. That's multivariate in this sense. And the distinction of whether you estimate this multivariate model using single level SEM with wide data or multi-level SEM with long data is sort of separate. Like, this is just concepts at this point. How to execute these concepts in the software depends on which one you're doing. And then, of course, I just sent an email the other day. There's a brand new thing that, of course, came out that just as if it wasn't complicated enough. So software and models are logically separate things. Don't ever let anyone tell you that something can't be done. The answer is always it can't be done in that software, but it probably can be done in life. You just have to figure out the right options or roll your own, as my husband would say. That means use Stan. Or NL mixed and SAS is what I use for any kind of problem where I have to write some kind of non-standard model and figure out what the parameters are. R has that in the Optim function, I think. Is that right? R users, does that sound right? Yes, I want to say so. There's roll your own stuff in R that's not Bayesian anyway. Okay, so relationships among random effects for individual differences. These are going to be your latent variables. Remember, in the multivariate specification, your fixed effects become means of latent variables. Your random effects are the latent variable variances. So we can talk about relations among intercepts. Are the predicted means at time 0 of two variables related? We can talk about relationships among time slopes or change, as I have in the picture. Are the predicted rates of change between two variables related? These are between person. So when we talk about this, it's people who. Like, people who start out higher on this variable start out higher on that variable. People who change more on this variable change more on that one. These are people things. These are summaries of longitudinal data at the between person level. The other part of it, though, and this part I think is originally was less interesting and lately has become a lot more interesting as people have figured out cool things to do with it, is relations among the residuals for within person variation. So this is like if I'm higher than expected based on my random effect trajectory at this occasion on one outcome, is the other one following suit? And so a picture I have that goes with this, here's some very noisy data. So we have a blue line and a black line for two different outcomes over time. And the slopes through them would look something like this to the best of my PowerPoint drawing ability. But the point of this picture is to say, hey, look what happened at time 3. They're way off their trajectory in one outcome, and look, they're also way off in the other. Like, whatever is happening at that occasion is some kind of process that's affecting both outcomes at the same time, like concurrently. It's also often of interest whether there's a lagged effect. So if I'm lower than predicted at time 2 on this outcome, does that show up at time 3 on the other one? Like, things take time to happen. Like, if I start feeling sick today and I start showing symptoms, does the effect of my sickness then show up more tomorrow? That kind of thing. If I decide to run a marathon today, my legs are probably going to be okay, but tomorrow morning is going to be bad. Trust me on this. I have run one marathon in my life. I was a postdoc. I did it at Penn State. It took me a little over 5 hours and it sucked, and I'm never doing that again. And part of the suck was not just the 5 hours, because you think that running is hard, right? We can agree on that. It's an effortful thing. But when you're outside for that long, it's like you're hungry, you're thirsty, you're chafed, like you're sunburnt, you're windburnt, and it's just like, ugh. But the worst part of it was that for the next 2 weeks in my little townhouse that had stairs, I had to slide on my butt down the stairs. Like my legs could not support my weight for at least 2 weeks after that marathon. There's a lagged effect for you. Half marathons, it turns out, are much more doable to fit into your life. Those involve a fairly minimal amount of training and recovery relative to full marathons. So there's my real world example of a lagged effect for you. It's very common in multivariate research questions to have questions phrased something like, does change in X predict change in Y? That kind of question is very common. But there's two different ways to answer it. One is the time slope part, the between person part, which is people who improve more than other people on this outcome, do they improve more than other people on that one? That's one way to answer the question. A complementary piece of evidence would be down here. Even after I control for what's happening sort of on a systematic level, what's happening on a fluctuation level? Do these outcomes appear to travel together over time? Does that happen concurrently, or is there a lagged delay of something happening? So those are the main ideas. Let me give you a couple examples. So these are two different outcomes in older adults. Functional change as measured by grip strength. Cognitive change as measured by block design, which is a matrix reasoning type of task. And I have the heavy black lines in these scatter plots here are the means for the sample. So if I were to standardize these two outcomes to the same scale, if I were interested in comparing them, just looking at these pictures, I might say, functional change appears to decline more on average than cognitive change. That's a comparison I can make by contrasting the size of the fixed slopes, and I can ask for a slope difference as a new linear combination. So it's like, which one declines more over time on average? That's one question. But then at the individual level, it's like, hey, look at this orange person who's super strong at the beginning. Is that the same orange person who's super smart over here? Like, do people who start out stronger, do they start out smarter? Doing better on this task. You can forgive me a little latitude with the language, right? This stuff is hard enough without having to go through all the, politically correct way of describing things. Stronger and smarter, that's what we're going to go with today. And likewise, is this, let's see here, let me find somebody. Is this person who fell off the cliff, the green line here, the same person, green line, that fell off the cliff over here? It took them a little longer. Like, those are the questions we're talking about at the between person level. Beyond just differences in fixed effects for the amount of average change, how does change correspond at the individual level across these outcomes? And if I were to, these are just observed lines. They're not smoothed out clearly. But then you can think about, like, well, this one here, they're going up and then down. Like, their overall trajectory might look like that. What happened then? Here's one from adolescent development instead. This is based on a study that was happening at Penn State, where they had a bunch of older siblings targeted, and then they got some extra money to target their younger brothers and sisters. So it was this, they were deliberately about 2 years apart. So we're looking at trajectories of risky behavior in the older siblings, who were measured from 12 to 17, and then their younger siblings, who were measured from 13, 14, and 15. So then we can ask, like, do the older kids increase more in their risky behavior? Kind of looks like that to me. But then we can also ask, let's say that we put the intercept at the end. Like, is this person who's going crazy all of a sudden, like, would this be their younger brother or sister? Like, the two outcomes are like observations of the family as the unit of analysis here, and the multivariate realization of that is the younger child and the older child. So, and then at any particular occasion, if you're higher than your trajectory expects, are you also higher on the other outcome as well? So, okay, 129. How are we doing, folks? Okay, just concepts so far. Now, several of you are doing something like this for a project, I think. Does this sound familiar to anyone? Correlated change? Maybe? Like, is that what I'm doing for my project? And there's at least a few that I read that I was like, yes, correlated change, this is what you're doing. Perhaps those students are not here, but my memory stands. By the end of this, I will know your projects better than you. That's what I do know. All right. So then, what is the problem with ignoring this idea? Let me go back, that we need these change circles. Like, what happens if we don't do that, especially on the X side? That's what this next slide is about. So if a time varying predictor itself shows individual differences in change, then those individual differences need to have their own circle, their own relationship to other variables in the model. Otherwise, you have an incomplete partitioning of what we were calling between versus within, as achieved via person mean centering or constant centering via the model. So what ends up happening is, like, if I think of the circles that are lurking within my boxes, okay? Let's say that this is my observed level 2 predictor, like the person mean of whatever over time. And here's the observed level 1 predictor, the within person deviation. So if we look at the bottom panel here, like what we were thinking of as purely within, because we subtracted the person mean off of it, right? We were supposed to have solved the problem. If people change differently, that green circle is still lurking here down in the level 1 variable. So any relationships that you would have at level 2 among changes in X predicting changes in Y are going to be confounded with whatever the within person relationship is at level 1. So let me put this back to the picture again. There we go. This green circle is stuck inside the purple one if you do person mean centering. In the same way that the original box has green and purple, because all these things were stuck inside it, if we only pull out this much, but there's still change variance, it's inside the purple. And that means what we were calling within as purple is two things at the same time. Level 1 within person, why are you off your line today? And level 2 between person, do you change more than other people? Those are two different variables at two different levels. And can you guess what happens if you don't pull out the green circle from the purple one? Yep, it's smushing. It's a new kind of smushing. I've made up a word for it. I'm calling it time smushing. We'll see if it catches on. The smushing that we started with was intercept smushing, because we're pulling out mean differences as a starting point. If we don't continue to pull out change over time differences, then it's time smushed. So this box is both the within effect and the between time slope effect at the same time. And interestingly, it's on the other time slope is where it shows up. That is a different problem than the partial overlap that we have up here. So what we were calling between person mean here is what the intercept variance would have had, but it also still has some of the residual. And the reason for that is because we're not letting the model pull these apart the way that we did on the Y side. So on the Y side, we have this relationship. The true amount of intercept variance starts with observed person mean differences minus this correction factor for how much of them are expected just based on random sampling fluctuation. So this thing is still kind of stuck in the person mean because we haven't let the model figure out how much is true relative to observed. So the Lutke et al. Paper 2008 was one of the first to tackle this problem. What's going to happen is that because this, like what some would call sort of error variance or fluctuation variance is lurking in here, the effect of the person mean is usually going to be smaller than the corresponding effect of what would become this green circle. So we go back to compare directly to make this point. This slope with a box that pretends the person mean is perfect is going to have a smaller slope than this one that understands the person mean is imperfect and tries to figure out how much of it is actually true variance as opposed to observed. That is a fairly well-known result. Now the downside. The more circles you have, the more people you need. The more likely your model is to break. So we talked about this on the last time, just an example. What if I wanted to know if this between effect differed between two groups of people? That's another box interaction, right? That's no problem. If I wanted to know if this between effect between two latent variables differs between groups, that's a latent variable interaction. That's a whole nother ballgame. So it's great in theory. In practice, it starts to become very complicated very quickly. Let's see, where are we at? Note to self, put in the purple and green slide right before, because I'm going to keep flipping back to it apparently. All right. Questions or comments? Any of this you want to hear again or differently? So this is covered in chapter 9 of the textbook. It's covered in, let's see, the under review article that I gave you. It's also covered, I guess, in the review article that's on your reading list from 2021 with my former student. So it's scattered across various places, these ideas here. But I also did a simulation in chapter 9. So if you don't have questions, I'll talk about that. So proof of concept.
Could you just give an example, like back to the purple and green slide of like
Yep.
what those variables would be? I think that would help me understand what all the boxes are corresponding to more conceptually, I guess.
Sure. So where we're eventually going to be is example 5b is going to have how parental monitoring in adolescence relates to changes in risky behavior in adolescence. And I simulated the data for this. I've done it a couple different ways, but it's based on a true pattern that happened that was interesting. So if X is monitoring and Y is risky behavior, if we put, I think in that example, I'd put the intercept at the end because the consequences of risky behavior for an 18-year-old are often much more serious than what they would be at age 12. So it would be like, do kids whose parents monitor them more than other kids at 18, do they have less risky behavior at age 18? Okay, that's this one. You could also have paths from the green intercept X over to the change circle for Y. So do parents who monitor their kids more than other parents at age 18, do their children have less of an increase, had less of an increase leading up to that point? Like, is monitoring a protective factor? Is it a good idea to keep track of what your kids are doing? Seems like it, maybe. If parents increase their monitoring over time, does that result in less of a growth of risky behavior over time? If I change my monitoring more than other parents do, does that show up in my kid growing less in this undesirable outcome than other kids? But at level 1, the relationship was actually opposite. So monitoring looked like it was a good idea at the between person level. But when kids are being monitored more than usual, their risky behavior was actually higher than usual. Now, which way does that go? Is it, get off my back, Mom, I'm going to show you, and then they go out and do something stupid just because they're being, controlled too much? Or is it, oh, wait, I've noticed my kid is getting into trouble. I'm going to start cracking down. I don't know which way it goes. But in the data, there was a negative relationship at level 2, and there was a positive relationship at level 1. So that's the story behind chapter 9, at least. I'm trying to think of other ones. Anyone else have a story? Doesn't have to just be me thinking of it. One of the projects I know is going to be looking at growth of math and growth of English language skills in high school students. So if I did it from that perspective, let's keep the intercept at the end. Do kids end up doing better in English than their peers? Do they end up doing better in math than their peers? That would be the intercept relationship here. If kids who improve more in math than other kids, do they improve more in English than other kids? And then when, after controlling for that some kids are just on a different trajectory, like in this year, like if your math scores were a little lower than usual, like what they're supposed to be relative to what your growth curve says, did your English scores follow suit? Like, was there something that happened in your life that sort of threw you off track and that showed up in all your outcomes on that particular occasion? Like they go together, or are they unrelated? Because if one went down and the other didn't, then that implies there's some other process at work that's uniquely affecting one outcome that's not uniquely affecting the other. Let's see, that's the other article I forgot about. There is an article in the Journal of School Psychology that's also on your reading list looking at student internalizing and math scores and which one sort of leads to which in terms of what came first. There's an example, the second example of that paper talks about that if you're interested. Those are the ones I can think of off the top of my head. These go by the name of parallel process models as well, multivariate growth curve models, latent curve models with structured residuals. That's another synonym for what this is going to be. There's a lot of words. There's very, very many words that these go by. Other questions? How about I save the simulation thing for next time then? That seem fair? Yeah, it's kind of a lot to process. Like it's honestly, it's hard to set up. So let's be fresh for that. You know, fresh on a garbage day was. Well, I think we got a better shot on it. It's because it's Tuesday. You see, you're not tired yet. There's a cliff for me that happens after Thursday, by the way. Like Fridays, my brain just doesn't work. So I don't know if that happens to y'all as well. Yeah. Okay. Well, then how about we call it a week? Y'all can get your homework done on time. Let me know if you need help. Office hours on Monday if you do. And then we'll see you next week and we'll keep working through this stuff. Okay, cool. Thanks for being here. Let me know if you need anything. Bye for now.